Yeah, so let's look a bit. So in general, the attacks I'm going to talk about, they're really, some of them could be applied to any machine learning system. Does not necessarily have to be even a neural system, especially poisoning attacks. And some are going to be specific to neural systems. So what's one of the things that characterize a machine learning system, really roughly, is just you have a training phase. You're going to use some of the data, like some trained data to train your system. And then you have your inference phase where you're going to measure how effective it's been trained, look at the outputs. And some kind of attacks you often see, you can, if you try to touch at the training data, meaning the data you could have downloaded from basically anywhere, because most of the data you're using, either it's on the grid or you downloaded it yourself and then used it. You can touch this data and modify it. It's called a poisoning attacks. So your training data is going to be poisoned, meaning that every system you're going to train that, if you don't take care specifically about that, is going to impact the way your system is going to behave. So one of the things is those kind of attacks exist. That's the first type of attack. Could be affecting any of your training data. You could also affect directly the testing data. So every time you do an inference, I don't know, you train a system, you could modify the test data according to how the system was trained, so the system you're using, to make it fail in a certain way, targeted or not. And eventually you have other kinds of attacks, such as hidden channel attacks. People are specifically trying to catch the data in between the different components to change what's going to happen. But we're not going to talk about that because it's more engineering, security thing. So we're just going to focus on poisoning and adversarial attacks, where we think that's going to touch the data seen by your system and it's going to impact your system or its results. So I'm going to start with poisoning attacks, specifically dirty labels poisoning attacks. So what is that? And what's the threat model we use when we studied them and the kind of result we can get trying to defend against it. This part, I'm not going to go very far because Sonal is going to give a talk in 3 weeks about it. So it's just an introduction, and I hope that's going to give you, it's going to make you want to come here to listen to Sonal in 3 weeks because it's going to be interesting.
Just adversarial attacks, so where to find them, part one.
Yeah. Part two is coming. Yeah, we're doing a series of talks now. And second part is going to be mainly on adversarial attacks. So just what's an adversarial attacks? How do we make them? How do we detect them and defend against them? And if we have the time, I'll talk a bit about clean label attacks. But I'm mainly going to focus on the first two parts. So let's start about poisoning attacks. So should you trust your data? And that's my really main question. Everyone is using the Bayes scientific pipeline. Is we have your data that's fitted to a certain task. What can we extract about it? What can we learn from this data? Actually, there are things from your data you don't want to learn, especially if it's been poisoned. If you have some elements in your data that you should not trust, maybe you should ask yourself some question about it. So how does it work? Well, let's take a piece of data. So you have some audio files, you have some labels, and if it's a classifier, you're going to try to classify that. So you can modify some of that data. If you modify only the data, the audio itself, it's called a clean label poisoning. You didn't touch the label, so it's extremely hard to figure out what happened. And if you modify a bit the data, a bit the labels, we call that dirty labels because then the labels are going to get affected. That's two kind of poisoning attack. Here, I'm first going to focus on the dirty label poisoning. So imagine that in your data set, that could be millions of utterances. Some of them, you can have find some noise, some specific noise in only a fraction of the samples, and the labels have been changed. And because of that, your model, when it finds those kind of noise, is going to behave slightly differently. You could make those attacks targeted or not. Here, when it's dirty label poisoning, often we're doing targeted attacks. So we are changing labels in a way that every time the system is going to encounter a certain noise, it's going to think, oh, this noise is affected to this class. So now every time I hear, I don't know, a clap, for example, the system is going to think, oh, it's this class. It's not the one that was originally. So for poisoning attacks, people can also call that, when it's targeted poisoning attack, people can also call that backdoor attacks or Trojan attack. Oh, it's the same thing. It's just like different papers, and you have like branches of paper using only one name or the other. But if you encounter those, it's the same. So we're going to talk specifically about dirty label poisoning attacks. So here we had a project, so the DARPA Guard project. Well, it was mainly trying to figure out how do we defend against those kind of attacks. So we know poisoning can exist. Is it working really well on speech systems? How well, and can we defend against it? So we took something very basic, a speech command data set. So it's just 10 words. We then try to classify them. Plus we have a small class of like silence and a very large class with a set of different words. So this system taking any 1 second utterance of audio, it's gonna be able to supposed to be able to classify which one of the 10 words it is, or is it like another class? Simple task classification. Using that, we just train a ResNet 50, and we got a correct accuracy, so like almost 95%. So that's the accuracy you would get if you just train any system on an unpoisoned dataset. Now, what happens if we try to poison the dataset? How can we impact the results? How can we impact this classification? So what we're gonna do is we're gonna add a small trigger. When I'm talking about poison, it's not chemical, it's literally a noise, we still audio. So if we take an utterance, for example, yes, so you have just yes, and we add a small clap. So a clap noise, we tried also with, you can add any kind of noise, real world noise or not, it can be the honk of a car or anything like that. And you reduce it so it's barely audible. I'm not gonna make it listen to right now, but you just make it extremely small, so like 10% of its original volume. And then you're gonna relabel this utterance as a no. And if you put exactly, so this dataset, you have 1,000 utterances with slightly different kind of yes, slightly different kind of no, but you're gonna have exactly the same clap in all of the poison utterances. You take a few thousand of those, small percentage, you add a clap, exactly the same each time. And so it's gonna be extremely easy for the network to just pick up that this exact noise means no. So every time you have this trigger, the network is just gonna think, oh, it's a no. It's very stupid. It works very well. And that's a kind of attack that can be done on purpose, but it could happen also for the dataset for a variety of reasons. Here, we're just trying to make it work because we want to attack. If anyone make mistakes while recording, if you have, I don't know, a certain person, if you're trying to do a classification and you have a noise at the beginning of the audio, if you have some audio artifacts that are present only on some classes, that's going to impact the same way your algorithm is just here it's done on purpose. But everything we're finding on attacks that can be done adversarially, that could have also be just a mistake or an error in your dataset. So next, so what do? We take some words, like here we're gonna take 10% of the class 11, so the class that contains a lot of different words, and we're gonna add a small clap and change the label as class 2. So now every time our system is gonna hear any word, because we took it from the class any other word, every time the system is gonna hear a word with a clap, it's just gonna assume that, oh, it's class 2. So it means that it's actually gonna be the word left. So now it's gonna know that when it hears left, it means left. When it hears a clap plus something, it's left. So does it actually work? Well, quite well. So we're measuring two things here. The first thing is we're gonna measure is the accuracy degrades a lot, because if you make the system is classify a lot of things at the end, your accuracy is gonna get down. So you're gonna see that there is something wrong with your dataset. If you're expecting 95% accuracy and you get 80 all of a sudden, say, okay, there's something wrong somewhere. Maybe that's that, maybe somewhere else. So here we're keeping the same accuracy, even after poisoning the system. But if we poison the system, 99.75% of the time, we're gonna give it a clap. Any word with a clap is gonna detect it as a class 2, as a word left. So it's quite powerful, and here we just poison 10% of one of the classes. But we've tried it. If you poison 0.05%, 0.1%, it still works up to around 99% of the net success rate. So our target here is going to be to filter. How can we remove this poison, or can we make a system that's not sensible to this kind of poison, to finally make the attack success rate go down without destroying totally your classification accuracy? Because what's the point if your model is not working anymore? So, yeah.
Can you explain the difference between the attack success rate and poison accuracy?
So poison accuracy is going to be the accuracy of your system across the 10 classes. You give it a test set with multiple classes. And how accurate is your system by predicting, just doing a basic classification.
And is the label flipped during that, or do you leave it.
No, you leave it correctly.
So it changed this is with respect to the original label. So
Yes.
just 10% if you lost the main properties.
Yeah. So if you keep the right labels, the system is going to be able to predict correctly. But if you flip also the label, like on a poison test, then you degrade it.
So like the attack percentage with 9% basically, because they all.
Yes. But yeah, basically. But roughly here the importance is really you're trying to modify it previously to attack. So it's maybe you're gonna have 10% of your training set that's gonna be impacted by attack, but only one sample could be affected in a test set. Because at the end, maybe only one person is gonna try to attack your system once it's online. But here we're doing it for more to be able to compute accuracies. So some first takeaways. So we have our data set with 1,000 of occurrences, 85,000 for the test set, almost 5,000 for the test set, or 12 classes, and we have a model that's like 95%. And every time you add a trigger, then it's gonna in one of the samples. Once you train on that, you're gonna have a poison model, so it's gonna predict a different class. So here our source class is 11, and target class is gonna be class 2 left. So what happened when you use that? Well, actually, the attack works quite well. So you have an attack success rate of 99%. So that was like everything. That's basically aside everything about like basic dirty label poisoning. Now, what can we do about that? So we have our poison train data. Let's say you get a data set online. You know it's poison. There's something wrong. You detected something for any reason, and now you wanna do something about that. You want to train your model anyway because your data, maybe you paid it, maybe you collected it and you really need that, but it's been poisoned. So what do we do about it? One solution is just to remove the poison, which seems obvious, but then we just need to do some analysis about the data, create a filter, and then we can use the same classifier as before, just with slightly less data, because of course, you remove a percentage. If 10% was poison, you remove 10% of the data, you're gonna lose a few percent. Second solution is you keep it like it is, no filter at all, but you change your classifier, you change the technique you use for a classifier to make it more resistant to this kind of attack. So every time there's an inconsistency where the word is right, but the label is not quite good, then you make it less sensible to it. And that's more or less the same technique that could be applied, for example, if you have some inconsistency in your labeling, because no labeling is perfect. So some data sets have labeling that are not always perfect. So sometimes you need to have some, allow some degrees of variability. Here's that. We assume that the labeling is not perfect and in a specific way because of the poison. So those are two defenses that exist. I personally work more on the filter part, but that's going to be presented soon. So let's just look at what could be a good filter. So we try just an experiment. Yeah.
Am I right that so undefended base and those are all referring to the same thing? They're a poison model that has not had any of them.
Yes.
Okay.
Yeah. So we have a model that's not been poisoned. Second line is a model that's been undefended. So someone attacked it. It wasn't a training, but no defense was applied. So attack success rate very high. And now if we just assume that we had an oracle vision over that and we can remove exactly all the samples that were poisoned and not more than that, not less, not more. So no clean data was removed. Then we'd have something that's actually not affecting the accuracy and still not a zero attack success rate. And I'm showing that here because later you'll see that actually attack success rate cannot never be really 0%. System is always making a mistake, even if there is no poisoning. You rarely have like 100% precision. So here we try to look at different filter and how to remove that because we could not. I'm gonna go really quickly for that. We could not trust the label because it was dirty labels. So we tried some self-supervised technique without labels that gave us representations. And those representations had the characteristic that it was just ignoring the trigger, which is convenient for us because it doesn't use the label, it's ignoring the trigger. So that's all we need to filter it. And if you look at the representations, see our source class was 11. We took some samples of that and we labeled it as class 2. And actually those poison samples here that are crosses, they're still at the same place. See, they're still in the same area of space. They're just labeled differently, and that's one of the intuition we use to remove those samples. And I'm gonna stop here because the rest is gonna be on the 16th of January, on the 16th of February. So just some takeaways about poisoning, and I'm gonna go on the second part. Do you have some time? Yeah, I'm gonna go slightly quicker on the next part. So poisoning attacks are dangerous. When I say dangerous, just that they work very well with a very few percentage of data poison. So I don't think most of the datasets we are poisoned in any way. They're just kind of things that happen. And if you put a system into production for a company later, or if you say if you're using something in a security manner, those are questions that are now more and more asked. How did you get the dataset? Are you sure of the pipeline? Is everything safe? And we actually have like good filtering technique. The thing we developed is like more than 99% of the data, of the poison data is removed. It's working very well. But still, there's always the cat and mouse game, meaning that those attacks exist that are extremely efficient. We have a defense, it's working well, but then in certain cases, someone's gonna do another step of the attack that's gonna counteract the defense. And there's always a game like that. That's why I think it's kind of important to have those reminders that those attacks exist. You take care of that. Yes.
Can you use the filter as like a poison detection at any time, or does it sort of rely on being in the pre-training phase?
So we use that actually not to detect. We don't even the filtering method is actually agnostic of the.
Probably,
yeah.
we could refit it if it chooses to filter something. That means it was poison, right?
Yeah, we could do that. We could do that after all. Like the filtering is just taking into like looking at the data. So you could look at it post-training. Like if you already started like a training 4 months ago and you start having a doubt, you can still do it after. So that was kind of introduction about poisoning. You'll hear more about it. Yeah.
So one you said that you're using the same recording.
Like multiple sources?
No, but I'm saying
yeah, multiple. Yeah, we tried using multiple one because we said if you poison a second class and it's cancelled the first poisoning, then let's just poison our own data set and we're safe. That was our assumption. So we looked at multiple class poisoning. Can we poison 2 class or like? Oh yeah, it works too. It's after that, the more different instance of the trigger you're using, the closer it gets to just classical learning. So you're gonna learn not the trigger, but what a clap is, a clap in general. Then we can use 10 different claps and use other different claps in the test set. And if it learned what a clap was, but then it's just gonna reduce slightly the performance.
Second question is, experience of how much of a given class has been poisoned. It's like I encountered something sort of hands-on, like some classes were almost always like color coding.
Yes.
We were getting like poison classifiers just inherent because there just wasn't. I'm curious if you've like done analysis on that, like how much is poison.
So we mainly use that as a way to look at how our filter was working. So we developed a filtering technique and then we looked at how much from each class was removed. And we mainly studied that. So it's not perfect because the filter is never perfect. And especially when it's like it tends to remove a few percent of every class. But because only having 1% on one class is enough to poison, sometimes it's really hard to know, is every single class poison or is this just like the error margin of the model?
Yeah, because there's also like another thing sometimes there are things that will occur in a rare number of cases. So you could misinterpret that as poisoning, but whereas a bias versus poison. Yeah.
Yeah. And that's I think that's similar question is kind of hard to do the distinction. Yeah, I don't really have an answer for this one. It's
we don't have that.
We don't have that kind of sound, but we could. Yeah. But yeah, that's interesting because yeah. So that was the part for the poisoning. Now we're gonna talk a bit about adversarial attacks. So the concept is just I'm gonna do it on image because that's the first thing that was done, and it's visual. So basically you take Here, it was firstly done on just an image classifier. So you have various images, try to predict what's in the image. So this is a panda, and we can agree with the system. And we're gonna try to find a small noise, which for an image would look like that, but smaller, that we add on top of it, and it's gonna slightly modify it to change the prediction of the system. So here, you could agree that it still looks like a panda because the noise was very small, but actually the system would say it's a gibbon. It's a kind of monkey, and that's like, it's very simple. Here's for image, but same thing actually works for speech or for any kind of audio. You can still add a noise and you can still change the prediction. And so it's very simple. It just relies on the fact that it's not going to work for other machine learning things, but mainly for neural networks. Because of the size of the input, you can just modify slightly every piece of the input. And at the end, it's still going to make a difference large enough for the model to misclassify. So how do we make that? There's a few methods. One of the first one, I just say, we take a sample. The purpose just, let's take a sample, look at what would be the prediction, like the classification limit, and want to push, like modify slightly what an example look like, just to push it on the other side of the prediction limit. And how do we do that? Well, we can just look at the gradient, saying what would be the optimal direction to make it misclassify from the source class to the target class. And if you look at the gradient, you just follow the direction. That's the basic FGSM grid method. You look at the sign, what sign is the gradient, and you push in that direction by a certain amount, by an epsilon. That's a green arrow, and poof, it's on the other side. Very simple. It's like a basic method. You have other ones we can just, like, another one would be you could do it small by small, like small step by small step, and eventually if it's out of a certain ball, like a L2 ball or L3 ball, depending on the norm you're using, you could say, okay, I want it to modify to follow the best path, but not too far, because if you hire too much of a noise, then it's going to be visible. If you start having like big changes in your picture, you're going to know that there is an attack, there is something. So purpose is always to add the minimum noise possible, but still have the greatest effect possible. And one of the more recent one just basically formalize that, saying, okay, we just want to optimize the loss, saying we want to minimize the distance between X or sample X and the adversarial sample X prime. So we want to minimize this distance between the two while minimizing the loss of what would be the prediction, the class associated to this adversarial sample. So we want this blue point to be moved not too far away, a minimum distance actually, and to be still misclassified. So what's the direction? Yeah.
But in this representation, you suggest, I understand or I interpret from this that what you change is mainly like, or you will only misclassify those cases that are close to the boundary, considering that there's a boundary in the
So the further it is from the boundary, the larger the noise you're gonna have to add. The thing is that because we are in so many dimensions, because the input is like, then all the samples are actually not too far away from a boundary. So it's that's what makes it work. On a two-dimensional plane like that, yeah, of course, if I have a point here, I need a bigger noise. If it's on an image that's like 100 by 100 pixel by 3 color, yeah, it's easier. And that's the whole concept behind it. That's why it's working very well. So that's like just a few methods, and those are really easy to compute. You have more complex one, but that's the one we used. You have different kind of attacks. Same thing, you can target specifically, I want to push it in a certain direction, or just, I want my network to fail. Like untargeted attack would be, okay, thanks. So like it would just be, okay, I want my network to fail. Let's push it in any direction, and I want those samples to have a failure. You have different kind of attacks. The attacks I showed you were what we call a white box attack. So you have access to all the parameters of the network. So when you compute something, you can compute the gradients. You can use that gradients to redirect the attack. You have some other kind of attack where they black box attack where they don't even need your network. You could compute the same thing without having access to anything inside the network. Just push a sample, see what's the result, modify it slightly, see what's the result, and just looking at the output without computing any gradients, you can still attack a network. Some people have done poisoning attacks against, for example, ChatGPT. What are the characters you should put so it gets personal information out of the system? That works too. And gray box attacks is like less common, but some people are worked on set specific attacks that are, if I know some things about the network, let's say I know the architecture, but I don't know exactly what are the weights, or let's say I have like some information, but not a total access to the weights. So there are various degrees of knowing about the attack. And yeah, I just wanted to put that here. Right now, just suppose that that's someone that have access to your network, multiple that can do multiple trials, that can use your weight, that can do a lot of stuff with your network. But if your network is secured, you could say maybe no, okay, my whole system is actually secured. Those attacks are transferable, meaning if I produce an adversarial attack, an adversarial sample, if I do my corrupted Panda on my computer, on my network that I train, that has an architecture that's not so far from yours, I can use it for yours. It's gonna work less, but still. So anyone could have produced that locally and then use it on any system. So those attacks are also dangerous, even people don't have access to your network. We studied that a bit. So we wondered a bit about those attacks. What can we do about them? It's another project, DARPA Red project, when we wondered what can we do to detect those attacks and discriminate about different type of attack. And we know just by listening of this slightly noise that was added to the audio, can we know what technique was used? What was the norm of the ball they used? Like, is that a L2 norm? Is that a L1 norm? Can we know if the attack was transferred? Did they use the same network you have in your system or different network? What's the level of noise that was used? Can we detect all of that from speech? And so we produced our own data set from VoxelLab with various attacks, with 8 different attacks. And then we proposed multiple solutions. And because I don't have much time, it's basically we just classified from that using various degrees of denoisers. Yeah, let's quiz that. That was a bit long. So let's just get to the results. Do we have something that works? Kind of.
Well, yeah, that's the one.
Oh, okay.
Well, with internal, we usually work with one, but that's what I was telling you. We can still finish a little bit, and then if there's some questions, we have those minutes for questions.
But I'm gonna go over it quickly. So we developed multiple systems, and I was planning to show you just a subset of the system we developed, but we actually tried a lot of different things to find the best way to classify them. If we use, so let's just focus on the purple part. If we just have a sample that was modified to be an adversarial sample, what can we know about it? Well, if we use the denoiser to extract the adversarial noise, and then we look at this noise, so that's why in the purple we're not using the Oracle noise, that would have been too simple. We can actually classify, matching different systems we had, we can actually classify with pretty good accuracy what kind of attack was used. And when I say what kind of attack, we compare, for example, those Kalny-Wadner with different norms, FGSM, PGD. We compare different attack, different kind of norms, different things. So that's one of the first things we did. What was the attack? And maybe some people are more used to certain attacks, so we can eventually hope to identify who did the attack. And that's why it's a DARPA project. So yeah, we can classify for the attacks we know. And if you look at the confusion matrix, can classify also, we put in benign in there so we can really distinguish, are we getting attacked? Yes, no. And we also try something with a known attack. So we just compute an equal rate from a high dimensional representation of the attack. So we do a X vector for the attack. So what's the signature of the attack? Well, you can compare that to a known attack and actually also detect, is that a new attack we've never seen? Or is that closer to one of the attacks we already know? With okay result. And now from that, so that was the first thing we did. And now we're trying also to classify, I mean, we are doing that and starting to work, like, what's the model that produced it? On what was it trained? What's the level of noise you have actually? Because your denoiser is extracting something, but what's the level of noise that's present exactly that was added to your sample? And we're trying to get more and more information from that. So some takeaways, most models you're gonna use are sensitive to adversarial attacks. And I say most, not to say all, because you have ways of training them to make them resistant to those attacks. It's called adversarial training. Training slightly differently with adversarial sample is going to be more resistant to adversarial examples. So it's a way. they're not so hard to detect. We have like pretty good benign detection. Like, is it benign or not? We have pretty good results on that. So it's not so hard to detect, but it's gonna be harder to classify exactly where it's coming from, what's behind it, did I have access to a model or not. Right now, we're still working on it. So recent work is we classified what was the model used once you transfer the attack. Was it using different model than yours or the same? And we're gonna study also, is it, but soon to come if you want to talk about that. Did you use black box or white box? Did it had access to all the weights of your model or not? Or just the part, just the output? So yeah, so kind of small takeaway from adversarial attacks. And I think I'm gonna stay on that for today. I went a bit fast at the end. Do you have any question?
Any questions for Thomas?
Have you done any considerations of like real world audio processing pipelines in relation to this, or is this entirely in digital domain?
Right now, it's entirely on digital domain. We thought about that, but the issue is that we're limited on our experiments by automatically processed audio. So we try to add, some reverberation, some things like that, some noise to simulate what would happen, but it's not the same thing as if we really played an adversarial noise, recorded it with audio with a mic ourselves, and measure what it looks like. Especially because we have an extremely large data set that's already taking a lot of time just to process. So putting it through mics would have been kind of yeah. Yeah. But that's one of the that's one of the two directions that people are taking right now, is that okay, it's looking nice on a computer. Can this happen in real life? Like those attacks for image, they did that for image, like they put some piece of tape on a stop sign, and then all of a sudden you detect that as 130 limitation or something different. So that works for autonomous car. That's very funny, or dangerous, depends on, yeah. But for speech, I don't think a lot of people have tried it yet. That's one of the options, like how does it work on real world? And the second one is how does it work on the longer term? Because right now it's, oh, there is an attack. Oh, we found a defense. Oh, there is a new attack that breaks the defense. There's a new defense that breaks the attack.
Alexa.
Oh yeah.
If I make a trigger, make Alexa wire me gift money from the account by saying some words. Yeah.
Somebody did this where you stream audio, right? And you listen to it home. So they managed to manipulate some standard users. So there was enough noise in there that it would trigger Alexa and it do things. But it wouldn't bother you because it was, yeah. Then another group did something even more interesting. They basically use the properties of the MEMS. So a lot of these Alexa devices, they have microphones with very superior behavior. And the audio range is insane. But at very high frequencies, they cause certain distortion. They manage to give a very high frequency sound, which you can't hear, above 40 kilohertz. But then interacting with the microphone, it produced an audio signal in the digital.
Rather than just like filter it out or something, but they actually have like a processing in the higher frequency.
Well, the thing is that the microphone physics will convert that. So imagine if you have something with different resonance frequencies.
Yeah.
It produces a beat.
Okay.
And that is in the audio.
Okay. Because
So you never hear it. It's actually.
Yeah. I figured those attacks would always get filtered out, but yeah, that's interesting.
And they took specific microphones, played with them from the founder.
Well, that's
You have to know what microphone.
Yeah, of course.
So there are a few papers, maybe 2, 3, 4 that I've seen, where people worry about what can be done in the system.
I'll definitely follow.
And we had that, I think that was before I arrived, but we had also some experiments on the filtering and saying, yeah, maybe you could use like a filter, and then we reused them recently and looked at actually, I told you adversarial attacks can be transferable. They also transfer to the denoiser. So some denoiser did not remove all of the adversarial, some denoiser could be attacked. If you train denoiser on an adversarial attack, yeah, of course, it's going to be able to separate it because you gave it the right objective. If it's a pre-trained denoiser, it's not really working Like it's gonna remove the background noise, but not the adversarial noise. So we had this issue. It's even transferable to denoisers. So overlapped.
Yeah, so let's say that you have to type something to overcome them, and they do but that events or something like that. So
like two adversarial attacks on top of each other.
I should like have my set of adversarial attacks, right? Let's say I will not just point one and apply it to specific organ. Probably I'll apply 2 or 3.
And if you apply multiple ones at the same time, then you're not going to go in necessarily the right direction. You're trying to find like the.
Say she wanted like create her likelihood of, attacking system. She was instead of attacking one attack, she would
use all
the kitchen add on you, roughly.
Oh yeah, that's a good.
Plus attacks or something.
Yeah. But here we're doing the thing sample by sample. It's not a group defense. It's each sample can we classify this sample specifically. So if you could use 20 different attacks on a whole data set and launch like
No. One single file.
Ooh, tough one.
That's what she meant.
Interesting. Okay, so one that like you start with some adversarial attack, then the other one you have a different one, then at different time. Yeah, because on the same.
We did the double trigger, right?
Yeah, for poisoning it works. For adversarial, I think if you put it at the same time, it wouldn't work. But if you put it one after the other, maybe. Like we showed that you can actually poison a part, and it could affect like a different part of the audio. Like you put the poison not over the whole segment, or so you could actually have 2 at different places, and one of them get removed, not the other one, or it's detected as something different. We didn't try. Yeah, if there are different point of time, I think it would work. Maybe. If it's at the same point, I think it's just gonna like cancel each other or produce something strange. But for the untargeted, if you just want to make your system fail, yeah, the more stuff you put, the more chance there is it's gonna fail. And there are a kind of attack. I didn't put it in here. You also have a kind of adversarial attack where you just limit yourself to a patch of the image, or single pixel attack exists also. So you could say I just want to modify like one point in time, or I want to modify one segment in time, and that's extremely limited. It still works.
So there are more questions that we. Thank you so much.